Hello, I'm Yutaro Hayakawa. Today I will introduce our work, Prism, Proxies Without the Pain. This is a joint work with the Michio Honda, Dr. Santry, and Lars Eggert. Our primary focus is Oceanstage systems. Oceanstage is a service which is provided by many popular cloud vendors like AWS, GCP, or Azure. The key feature is a flat namespace where objects are identified by URL and retrieved with the simple HTTP GET request. Let's think about how to scale out the Oceanstage systems. Front-end proxy architecture is common today and easy to implement using existing software like NGINX. The front-end terminates the client connection and rewrites the request payloads to and from the backend. Different requests in the same client connection can be relayed to and from the different backend, so it achieves the request granularity backend selection. The problem is the inefficient utilization of network and CPU, which we will show later. Next option is content-based routing approaches based on programmable switches like SwitchKV, Netcache, or Pegasus. These approaches have the switch understands and relay the request at the network line rate. Oceanstage systems would have the switch act as a front-end, but unfortunately this approach doesn't work because we must support large encrypted data delivered over the standard protocols, including TCP and TLS. Our approach is connection handoff to take the best aspects of the front-end proxy and content-based routing architecture. In this architecture, the front-end does relay the request, but not the response data. Thus, reduces the attachment link utilization. Also, the front-end does not encrypt the traffic, thus reduces the CPU utilization. Prism is based on TCP handoff, which moves established TCP connection from one host to another. At the high level, a front-end first accepts the client's TCP GET as usual. It then forwards the request to the backend, but together with the serialized TCP connection states, like TCP sequence numbers and negotiated TCP options. The backend then restores the TCP connection and returns the response to the client directly. The switch rewrites the source address of the packet to the front-end one, so client never notices that the peer host changed. Actually, this is not new. It has been proposed multiple times since 1998, but as of 2021, it is way more feasible than as of 1998, because Linux supports TCP connection serialization and the programmable switch have become popular these days. So how Prism improved the performance of the front-end proxy-based Oceanstage architecture? We made a simple Oceanstage system which implements a subset of S3 protocol and measure the performance with front-end proxy architecture and Prism architecture. In front-end proxy setup, we use NGINX in both of the front-end and back-end servers. We use WLK for generating the benchmark traffic. It fetches the in-memory object of backends through front-end proxy with 100 parallel TCP connections. In this benchmark, all of the backends have the same replica of objects, and front-end simply round-robin the client's requests. The results for the front-end proxy setup is like this. We evaluated it with two metrics. The first one is the cluster CPU utilization, which showed with the left y-axis and bar graph. It shows the total amount of the CPU resource utilization for entire cluster. In this case, the maximum amount of the cluster CPU utilization is 1,200% because each service has 2 cores and there are 5 backends and 1 frontend in this setup. The other is a throughput measured in client side, showed with right y-axis and line graph. We measured them with various object sites showed with x-axis. To summarize the results, front-end proxy-based setup showed 3 major problems. The first problem is the throughput of the entire cluster is tied to the bandwidth of the front-end proxy in case of the large object transfer. The second problem is the front-end CPU usage hits the limit in middle to large object size. And as a result of those two, most of the backend resources are not utilized. This is the third problem. We have more detailed analysis of why this problem happened in our paper, but we confirm that either the attached bandwidth or the CPU resources of the front-end proxy become the bottleneck in this workflow. So how these problems are improved by using Prism? The results look like this. First, since Prism bypasses the front-end in return path, the throughput no longer tied to the backend bandwidth of the front-end. It is almost free utilizing the uplink bandwidth. With the same Prism, it also dramatically reduces the CPU utilization of the front-end. Instead, the CPU-intensive tasks like TLS processing or the data transfer are distributed to the backend. As a result, Prism effectively utilizes the backend CPU resources. This experiment demonstrates that TCP handoff-based approach is very effective for improving the performance of front-end proxy-based object storage architecture. Achieving the Prism was not easy, and here's our contributions. The first contribution is a robust handoff protocol, which requires much stricter design than the original one to take advantage of the modern Linux stack and programmable switch. The second contribution is UDP-based switch design. Since Prism requires frequent rule updates, each consists of multiple commands, it was important to update the rules quickly within the data plane and atomically across multiple rules. The third contribution is stack. Prism doesn't require client change, but it does require the significant server application change. We designed and implemented the software stack to hide the vast majority of the complexity to use Prism, which spans across the switch communication and host kernel module. Finally, we implemented two variants of the object switches with Prism and evaluated them using heuristic YCSB workloads and level DB storage backend. In the rest of this talk, we mainly focus on the first contribution. So now let's take a look at one of the issues which made us redesign the TCP handoff protocol from original one. Please consider the situation that front-end server got the request and started to hand off the TCP connection to backend server. And right after that, client sends the unexpected packet. The problem in here is while migrating the TCP connection, there's a small moment that no one owns the TCP connection. If the packet from the client comes at this moment, what happens and who should receive this packet? If we migrate the TCP connection before configuring the switch, it reaches to the old server and should be reset. So how about migrating the TCP connection after the configuring the switch? It also doesn't work because the same problem will happen in new server side. To avoid this situation, we need to add one more phase to block the traffic from clients. In first phase, configure the switch to block all traffic from clients. Then after connection migration, set up the actual address translation rule. We call this two-phase handoff protocol. By this extra step, we can avoid the corruption of the TCP connection by unexpected packets from client. However, the concern in here is the cost of this handoff procedure. We measured the latency of each step of handoff in our prototype implementation. Here's the result. In total, it takes about 232 microseconds in average for handoff. We believe it can be improved more, but the important thing in here is the latency of the handoff is almost fixed. So how it costs depends on how much of the total request latency spent for the handoff. In object storage use cases, total request latency highly depends on the object size. So if the object size is larger enough, the 232 microseconds of handoff latency should be negligible. So how large does the object size needed to amortize the connection handoff cost? This graph shows the compared throughput of the Prism and NGINX-based front-end proxy setup. The benchmarking scenario is the same as before. Here we have the points that the throughput of the Prism outperforms the one of NGINX proxy. In case of HTTP, it is around 2 kilobytes, and in HTTPS, it is around 16 kilobytes. We believe it fairly covers the realistic use cases. So here's end of our presentation. We presented the performance issue of the scale-out object storage systems, which is caused by the front-end proxies to mediate all the traffic. We solved this problem by designing new TCP handler protocol and stack, which address the issue in taking advantages of modern Linux kernel features and programmable switches. Our source code is publicly available. Please visit this link to get it. Thank you. I'm happy to take questions.